Alright, so here we go into a video on the student's t-distribution, which is also just known simply as the t-distribution. Now, all the other videos in this series on distributions are up on zedstatistics.com should you choose to watch them. I've done the Poisson, the binomial, hypergeometric and normal. But this one's really interesting, and it's to do with a distribution that you meet early on when you're dealing with statistics, and it's often misunderstood. So this is how this video is going to pan out. We're going to start with an overview, which will give you a sense of what the t-distribution is actually used for, and in particular how it comes out of this thing called the t-test. And the one thing we're going to learn here is that the purpose of this t-test and the t-distribution is for dealing with small samples. So that kind of behooves me here to then go on to a bit of a sampling recap, because I want to be able to put this knowledge of the t-distribution into context. So that'll give you a bit of an idea of what problem the t-distribution actually solves. We'll then have a look at a visual comparison of the t-distribution, in particular against the standard normal distribution, or the Z distribution if you like. So of course that'll give you a good sense of what it looks like across varying degrees of freedom. And finally, we'll assess how to calculate both probability distribution functions and the cumulative distribution function as well. So I'll give you a heads up here on how to use Excel formula to run calculations for the t-distribution. And also, of course, how to use tables, the old t-tables, which I'm sure one day are going to be banished to the history books. But still, some universities are using t-tables, so I want to make sure that we know how to use them as well. All right, so let's get down with this overview. Okay, so the t-test was developed in 1908 by this guy called William Seeley Gossett, a dapper young gentleman indeed, who came up with this thing called a t-test, which solved a problem they were having at the time in statistics of dealing with small samples. Now, there's an interesting story about this guy. Now, he was actually working as a chemist for the Guinness Company, brewing some thick, dark beer in Ireland, when on the side he was doing a little bit of work for the famous statistician Karl Pearson. So Gossett ended up writing a paper on this small sample solution, but because he was working for Guinness, Guinness didn't allow him to use his actual name because that would give away the fact that Guinness was employing a statistician. And they didn't want other people to know that they could get a lot of benefits out of hiring a statistician. And they pretty much figured that that would help only their competitors. So they required that he use a pseudonym, and his pseudonym was Student. Hence why it's called Student's t-distribution and doesn't bear the name of the guy that developed it. Anyway, so the problem that he was solving was when we knew the underlying distribution as normal. So let's say we're just talking about people's heights, right? It's a pretty reasonable assumption to presume that heights might be normally distributed, say within a particular sex. However, if you didn't know the population standard deviation, and you only had a small sample with which to estimate that, there were some problems that arose. And we'll have a look at that in a bit more depth in our second section of this video. But it's these three scenarios occurring that necessitated a solution. A normal distribution underlying, with an unknown population standard deviation, and if your sample size is too small for the central limit theorem to apply. Now, essentially what the central limit theorem says is that if your sample size gets large enough, we can just use a normal distribution for our sample statistic. But if it's too small, the central limit theorem is not applying yet, so what do we do? The dapper young Gossett suggested we use something called a t-test involving a t-distribution. Now, here are some measures that would be t-distributed. And if you've dealt with any statistics before, these will be quite familiar to you. So this is what would be called a one-sample t-test. And if you're keen on seeing a completed one-sample t-test, I'll put a link up here for one of my other videos where I do exactly that. But essentially here we're trying to use a samples mean to test a hypothesized population mean value. And of course here you'll note that in the denominator we actually have the sample standard deviation, because the population standard deviation would be unknown. This second one here relates to regression, And again, it's the same idea. We have an underlying normal distribution, which is assumed. The population standard deviation is unknown, and that's implied within this standard error here. It's the standard error of the sample gradient. And if our sample size is small, we're going to need a t statistic or a t distribution for this particular statistic here. And this one on the right is maybe what you would call a two-sample t-test, where we are assessing the difference between two different populations. So this guy's work is now used in a lot of different scenarios throughout the statistical practice. And any introduction to statistics course will have you dealing with probably all three of these measures. All right, so let's just go back a little bit and have a look at sampling in general to see what problem the t-distribution is actually solving. So here let's just say I've taken a sample of 5 observations from a normally distributed population. And the example I'm giving here is the heights of female basketballers, which may indeed be normally distributed with a mean here of 180 centimeters and a standard deviation of 10 centimeters. So if I take a sample of 5 observations from that normally distributed population, let's just say I get these 5 heights. Now I could place those heights on the distribution here as these yellow crosses. And you can see that generally we've selected a sample that happens to be a little bit higher than the mean on average, right? And if I was to ask you to find the average of that sample, quite simply we're just adding everything up and dividing by 5, and we'll find it's 187.2 centimeters. Now the question is, how would such a sample mean be distributed? Now if we can assume that the underlying distribution is normal, then the sample mean will also have a normal distribution with a mean of mu, which is the true population mean, and a standard deviation of sigma en root n, sigma being the population standard deviation, and n being the sample size, which in this case is 5. So if I was to repeat taking this sample, say 100 times or 1,000 times, the distribution of those sample means would look a little bit like this. And don't be confused by this squared here. That's just the convention of how you write this sort of distribution notation. This second term here is the variance. So the way I write the standard deviation is by putting it in brackets with a big squared out the back. So great, we know that the sample mean will have a normal distribution if the underlying distribution is normal, and we know the population standard deviation. So let's see what happens when we relax that assumption about the population standard deviation. So say we were interested in testing the population mean value of 180 centimeters by using our sample. Now in this case, we would set a null hypothesis to be that the true population mean is equal to 180, and our alternate hypothesis would be that the population mean is different to 180. So we're putting that null hypothesis to the test here, and this was our sample, 183, 170, 189, 191, 203, with a sample mean of 187.2. Now in conducting this test, we would use this z statistic here, which is x bar minus mu over sigma on root n, which essentially figures out a standardized measure of how extreme our sample is if the null hypothesis is true. You can see we've got 187 up here minus 180, and you standardize that using the population standard deviation and the number of observations. So that, as I said, would be a normal distribution, and you could theoretically conduct a test using that z statistic if you knew the population standard deviation. But of course we don't. We have to use s here in place of sigma. That's the sample's standard deviation. So here I can actually calculate the standard deviation from these 5 observations here, and I get 12.05. Now unfortunately, this statistic we've created is no longer distributed as a standardized normal variable. And the reason is we actually have a little bit more uncertainty in this estimate of the standard deviation. Given it's come from a sample, we know that a different sample of 5 basketballers would give us a different estimate of the standard deviation. So instead of getting 12.05, maybe with another sample we might get 8.6 or something, right? So there's an extra degree of uncertainty in this estimate of the standard deviation, which means that the distribution of that whole statistic must get a little bit wider to accommodate that extra uncertainty. And it's the t-distribution that provides that extra width, so to speak, over the normal distribution. Furthermore, this uncertainty that we have around the standard deviation actually depends on the number of observations we have in the sample. Think about it this way. If we have a heap of observations, say we have 50, 100 basketballers that we've sampled, the standard deviation that we get from that sample would be a pretty accurate reflection of the true population standard deviation, right? So in that scenario, this t-distribution should look a lot like the z-distribution. But when you only have a small sample like we have here, you are actually losing a little bit due to that estimation. So that's why with a t-distribution, it has this thing called degrees of freedom, which depends on the number of observations. So you'll get a different t-distribution depending on the number of observations that you have, because that ultimately defines how much extra uncertainty we have with this estimation. So to summarize, the t-distribution is required because we need to adjust for the additional uncertainty around S, the standard deviation from the sample. And the second point to note is that the smaller the sample size, the more uncertain we get about this estimation. So the more different this t-distribution will need to be from the z-distribution. And we'll see how that operates in the next section. But nonetheless, we could now calculate this t-statistic by going x bar minus mu divided by the standard deviation from the sample on root n. And this would be distributed as a t-stat with 4 degrees of freedom. 4 because there are 5 observations and the degrees of freedom is n minus 1. Okay, so let's have a look at some visualizations of the t-distribution with varying degrees of freedom. Okay, so what we can do now is have a look at how that t-distribution looks in comparison to the z-distribution. And this is a t-distribution with those 4 degrees of freedom. And you can see indeed that it has fatter tails and it's also less peaked at the top, right? So in other words, that extra uncertainty we have means our distribution is pushed outwards a little bit. We have more of the distribution in the tails. And you can see that if we drop the degrees of freedom even further, there's degrees of freedom being 3, being 2, being 1, which is just literally having 2 observations in your sample. So clearly when you have only 2 observations in your sample, you can't be that certain about that estimate of the standard deviation that you're using in these formulas, right? So the t-distribution is really going to flatten out hard here. And if we go back in the other direction, there's 2 again, 3, 4, and we can keep pushing to see what it looks like when the degrees of freedom gets significantly higher. And I'll stop at about 20. So you can see what's happening. As the degrees of freedom gets larger and larger, this orange curve here, which is the t-distribution, approaches the white one, which is our z, or standard normal distribution. And that makes sense too. If you have a sample of 20 or more, you're starting to become quite confident about your estimate of the standard deviation, right? You no longer need to adjust that much for this lack of information that you have. So eventually, as the number of observations and thus the degrees of freedom keep increasing, the t-distribution will eventually become, at the asymptote, the z-distribution. Okay, so let's get stuck into some calculations now using largely Excel functions to help us. And we'll also look at using t-tables as well. Okay, so how do we actually define the t-distribution? Like, what is the formula that gets us this curve, which we call the t-distribution? Well, this is our probability distribution function. And I ain't getting into this too deep, trust me, but I just wanted to show you that there is a formula that defines the height of this curve at any given point. And it's got a gamma function in there. It's actually got 2 of them. And here's our value of x and a few n's, and geez, it's not a very friendly formula in there, is it? But thankfully, you never have to use this formula. Any statistical software will calculate that for you. And even Excel has these handy statistical functions, one being t.dist, And the way you use it is by just subbing in any value, so any value on the t-distribution, telling it how many degrees of freedom you have, and also by saying the word false here, we tell it to provide us with the PDF, the probability distribution function, in other words, the height of the curve. And in fact, that's the formula that allowed me to produce those t-distributions on the plots earlier on. Now, more likely, you're going to be using the cumulative distribution function, which is not so much the heights of a given point, but the area to the left of a particular point. In other words, how much of the distribution has elapsed at a particular point here. So if we were to try to find the cumulative distribution function at this point, we could use tdist again, providing the function with the value of x, which would be this number here. It might be minus 1.8 or something. The number of degrees of freedom, and we say true here, which tells Excel that we want the CDF, in other words, the area to the left of this particular point. Now we can actually use these formulas in reverse to answer really important questions like this. What proportion of the t-distribution, let's just say with 4 degrees of freedom, exists above t equals 1.61? So here's that t-distribution again, there's 1.61, and we want to know how much of the t-distribution lies above this point. In other words, how extreme is our sample here, or how extreme is this t-statistic? And the way we can do that is by going 1 minus tdist, because don't forget, tdist gives you the area to the left of a particular point. So 1 minus tdist, providing it with 1.61 and telling it 4 degrees of freedom. True tells Excel that we're after the CDF. And it gives us the answer 0.091, indicating that there's 9.1% of the distribution above this point. So in other words, if you got a sample statistic of 1.61, you'd now have a good sense of how extreme that is, and whether or not that would require you to reject the null hypothesis. Now, another common usage is to ask what t-statistic, again with 4 degrees of freedom here, provides 2.5% in the upper tail. So let's just say we want to know this point here, above which lies 2.5%. Now here we use the t.inv function in Excel, which requires us to tell it what CDF we require and the number of degrees of freedom. So in this case, we put in 0.975 here, because if there's 2.5% in the upper tail, there's 97.5% below that particular point, right? So t.inv will provide us with the answer here, given it at 2.78. So the t-statistic of 2.78 relates to the point above which lies 2.5%. And because of the symmetry of the t-distribution, don't forget the middle of this distribution is 0, negative 2.78 will be the point below which lies 2.5%. And hopefully you might be seeing what I'm getting at here. If there's 2.5% in each of these tails, you have 95% in the middle. So this is the important t-stat to use if you're trying to find a 95% confidence interval where there are 4 degrees of freedom. Now, this is exactly the way you should be solving these questions in 2019. But I know some university students watch this channel and they've been on my case sometimes about not showing them how to use tables to find these values. So I'm going to come through for you, university students, and I'm going to show you how to find those values. Okay, so here we go. This is a t table, which will always look a little bit like this. It'll have the degrees of freedom down one side and the level of significance up the top here. So if we want to know the t-statistic above which lies 2.5%, we can follow this along to 2.5%, that's 0.025. We can scroll down to where the degrees of freedom is 4, and here we go, 2.77645, or to 2 decimal places, 2.78. So that's indeed how you might find this value, 2.78. All right, so there you have it. That's my video on the t-distribution. If you like these videos, feel free to subscribe, and you can check out my website, zedstatistics.com, for a whole heap of other videos, including the rest on this series on statistical distributions. But I'll see you later.